I'd like to reformulate the problem from last time so that we're working over projective space. So as yesterday, I'll be working over an algebraically closed field. Only today, I'll pick a finite set of points from projective space. And at the beginning, I'll assume the dimension is n. So I want to blow these points up to obtain a new variety. So this is the blow up of the points in S. So I want to look at the divisor class group of the resulting variety. So I'll denote that this way. To indicate I'm blowing up the points of S, I'll use a subscript S. These are the points I'm blowing up. This is the divisor class group, by which I mean divisors modulo linear equivalence. And so this is a free abelian group of rank S plus 1. It's we can take as its generators the class of a hyperplane plus integers times the classes of the points blown up. So H is the pullback of a hyperplane class. And the E's are the classes of the inverse images of the blowups. And so here's a, let me redefine the effective submonoid. So for today, the effective submonoid is going to be the submonoid of the divisor class group generated by classes of effective divisors. And so here is the same problem that we were looking at yesterday, only expressed in what's probably a more common way. So the problem from yesterday was asked by Velasco and Eisenbud just about a month ago. And the question was, given a set of points and a divisor in the a divisor class in the divisor class group, does there exist a finite computation? I guess I really mean, does there always exist? Does there always exist? Oh, I put the always in the wrong spot. Does there always exist a finite computation to determine if R times F is in the effective submonoid? For some positive integer R. And this is an open problem. What we talked about yesterday was some cases in which there were finite procedures to decide this question. In particular, the one I wanted to talk about today is if the effective submonoid is finitely generated with known generators then there is a decision procedure. In particular, if you know the generators, and if there are only finitely many, then if you take the effective submonoid and tensor it with Q, this will be a cone. It'll be a polyhedral cone defined by finitely many linear inequalities. And in that case, RF is in the effective submonoid for some R if and only if F itself is in the cone and this you can tell just by checking the finitely many inequalities. So it's a fairly difficult computation, actually, to take generators and turn them into linear inequalities to cut out the cone. But in principle, it's doable. So the question is, of course, maybe there are other times when you can answer this question, but certainly when this thing is finitely generated, you can answer it. And so I wanted to look at an example, a fairly classical example, where it is finitely generated. And that example was the case of points in the plane when there are too many points. So let's look at the case of n equals 2. So we're looking at the projective plane. In the case of the projective plane, we have the intersection form. On the blow-up. So this is defined by the fact that, in this case, a hyperplane is a line. The intersection of two lines is a point. So h squared is equal to 1. The intersections of the blow-ups is negative 1. H dot EI is 0 for all of the exceptional divisors, and any two different exceptional divisors are also orthogonal. And so this extends to a quadratic form on the divisor class group, which we'll make a lot of use of. Let me also define neg of x. So I want this to be the classes of prime divisors of negative self-intersection. The set of all prime divisors, by which I mean effective, reduced, irreducible divisors. The set of, I should say, classes of all prime divisors C of negative self-intersection. So the negative curves. This can be infinite in general. If S is greater than or equal to 9, then this set of negative curves can be infinite. The easiest example is there can be infinitely many C with C squared equals -1. If S is greater than or equal to 10, there can even be infinitely many C in neg x with C squared equals -2. So related to this, there's an old conjecture, another difficult conjecture. So the number of negative curves can be infinite, but what about how negative they are? How infinite can that be? This is an old conjecture. I don't know who it's, yes?
Is it easy to see why only happens when S is 9?
Oh, that you can't have this happening?
Let's say -1.
Well, for S greater than or equal to 9. So if I'll give you some indication of why there can't be infinitely many when it's 8 or less in a couple of minutes. The basic reason is that the quadratic form is not negative definite. But if you look at the canonical class, which is an important class, the space perpendicular to the canonical class is negative definite if S is less than or equal to 8. And that negative definiteness prevents there from being infinitely many. When S is equal to 9, it's only semi-definite. And when S is bigger than 9, it's a fairly complicated space. But you'll see in a little bit, at least you'll see some indication of why this is true. I won't explain where the -2 curves can come from, because that requires looking at some fairly special configurations of the points. But the reason I mention the -2 is because it's not just -1. You can also have infinitely many -2. I'm not sure how many. I don't know offhand if you can have infinitely many that are -3. But one question you can ask is this folklore conjecture, which is that for any S, there is an integer, I'll call it lambda sub S, such that if C is a negative curve, C squared is greater than or equal to lambda S. So the conjecture is that there's a lower bound for the self-intersections of the negative curves. There could be infinitely many negative curves, but conjecturally, they can't be arbitrarily negative. They can't have self-intersections that are arbitrarily negative. And I don't know who this is due to. It just seems to be, there are no counterexamples at this point, and people just seem to know that this seems to be what's true, but nobody knows how to prove it. As another conjecture, here's a more specific conjecture. And I don't know who this is due to either, but it certainly, I'm sure people noticed that this seemed to be true, even though there's no proof for it at the moment. If S is a set of S greater than 9, well, in fact, if S is a set of S greater than or equal to 1 generic points, then we can take lambda sub S equal to -1. And this is known for S less than or equal to 9. So in other words, if you blow up generic points in P2, the self-intersection of a negative curve is always -1. And that's definitely true if you blow up at most 9 points. If you blow up more than 9 points, it isn't known to be true, but it's expected to be true. In P2, yeah. So I'm now just working with P2. Yeah.
Is there a difference if you assume the field is C? Is this known then?
No. It's in fact, it's more likely to have a counterexample in characteristic P than in characteristic 0. So let me state a more general conjecture, slightly more general conjecture. A more general conjecture would be for any smooth projective algebraic surface X, there is a lambda sub X such that for any C which is reduced and irreducible, we have C squared greater than or equal to lambda X. So it's, I should say one more thing. If we assume characteristic 0, this is an open conjecture. But there are counterexamples. There are counterexamples in positive characteristics. And in fact, some of the counterexamples are in Hartshorne's book. So if you look carefully at the exercises, one of them gives counterexamples in positive characteristic. But in positive characteristic, it's still an interesting question because I think the counterexamples don't apply to blowups of the projective plane. And so I actually believe that this conjecture is true for blowups of the projective plane over any algebraically closed field in any characteristic. The question here then might be, for what surfaces does this conjecture fail? And so there are some examples in positive characteristics where it fails. But there are no known counterexamples over the complex numbers, or at least none that I've ever heard of. So that would be an interesting thing to figure out. But I want to focus on the case of blowups of P2 at a finite set of points. So let me look a little bit at what is known for the case of a blow-up at a finite set of points when we have a finite set of points in the projective plane. So the first thing is, I want to define a submonoid that's a little bit bigger than the effective submonoid. So I'm getting tired of writing the subscript. So from now on, x is x sub s. So gamma of x is going to be the submonoid of the divisor class group generated by the negative curves and by the anti-canonical class. And the anti-canonical class is cubics passing through the points, or at least formally. So it's 3 times the class of a line minus the blow-ups of the S points. Then the fact is that this contains the effective submonoid. And sometimes it's actually equal to it. It contains the effective submonoid with equality if and only if the anti-canonical divisor is in the effective submonoid. And it's hard to find. I'm sure this was familiar to Nagata, though I don't think he stated it this way. The key ideas for why this is true are due to Duval and Nagata. But in any case, this gives us a handle on the effective submonoid. We know it's contained in here. It's typically not going to be equal, but in some cases, when the anti-canonical divisor is effective, we do have equality. And so this allows us to say something with respect to the number of points we've blown up. So for item 2, let's look at the case of more than 9 points. When we have more than 9 points, it's possible that this is effective, but it doesn't have to be. Because what we can do is you can have any number of points that you like and just blow up points on a cubic curve. And in that case, this will be effective. But typically, there won't be a cubic curve through 10 or more points. So sometimes this is in here, but it doesn't have to be. And also, the set of negative curves need not be finite. But it could be finite, depending on what points you pick. So the next case would be 9 points. When you blow up 9 points, minus k is always in the effective submonoid. And this is true by Riemann-Roch. So that's automatically true. However, the set of negative curves needn't be finite. It could still be infinite. But when you blow up 8 or fewer points, then everything is nice. So in particular, when you blow up 8 or fewer points, then this is in the effective submonoid. And the set of negative curves is finite. And since minus k is in the effective submonoid, that means that the effective submonoid is equal to this other submonoid, gamma. And gamma is generated by the anti-canonical divisor and the set of negative curves. So it's finitely generated. But in fact, we'd still like to say a little bit about what exactly are the curves in this negative submonoid, or this set of negative curves. If you want to answer the Velasco-Eisenbud question, you not only want to know it's finitely generated, but you also want to know what the generators are. And so that's relatively easy. In fact, so let's say S is less than or equal to 8. What classes can occur as elements of the set of negative curves? And the answer comes from the adjunction formula. So the adjunction formula says if you have a reduced irreducible curve, it tells you what the arithmetic genus is in terms of intersections with the curve itself and with the canonical class. So in particular, c squared is equal to twice the arithmetic genus of the curve minus 2 minus the intersection with the canonical divisor. And so if C is a negative curve, then you get that C squared is less than 0, but it's got to be of this form, and the arithmetic genus is non-negative. So that constrains the possible self-intersections that you can get. In particular, well, so there are two cases. So for the first case, it's certainly possible that C meets negative k negatively. And so in that case, C will be of the form T times H minus M1 E1 minus etc. with T less than or equal to 2. And it's less than or equal to 2 since minus K is 3 times H minus E1 through ES. And minus K is an effective divisor. It's the class of an effective divisor. And if C meets it negatively, that means that C is a fixed component. And in particular, that means that minus K minus C is effective. So this self-intersection being effective forces this to be effective. And so that means that the intersection with the class of a line is greater than or equal to 0. And the intersection with the class of a line, H meets negative K 3 times, and H meets C T times. And so this means that this thing is greater than or equal to 0. But in fact, it can't be true that 3 is equal to T and have this intersection be negative. That takes a little bit extra work. So it turns out that this has to be at most 2. And if this is at most 2, the multiplicities of the points that you blew up can't be bigger than 2. You can't have a polynomial that vanishes at a point to multiplicity greater than the degree. So that also means that the multiplicities are bounded above by 2. And so therefore, there are only finitely many possible classes for this curve C in this case. So basically, what this is saying is that a cubic curve, if it contains a component, that component has to have degree 3 or less. So this is case 1. Case 2 is, well, suppose the intersection is non-negative. Well, if the intersection is non-negative, what you have is two non-negative terms here, and you're subtracting 2, and it's got to be negative. So that means that c squared is either negative 1 or negative 2. So the only possible solutions are the only solutions to the adjunction formula is c squared equals c dot k equals negative 1. And in this case, the arithmetic genus is equal to 0. Or c squared equals negative 2, and c dot k is equal to 0. And again, the arithmetic genus is equal to 0. Well, it turns out that because we've blown up only 8 points, the space, so by k perp, I mean all classes in the divisor class group such that f dot k is equal to 0. It turns out that k perp in this case is negative definite. Well, in the second case, we have c dot k equals 0. So that implies that c is in k perp. But c squared equals negative 2. And so it's got to be within, in some sense, this is negative definite. This has distance, the square of the distance is negative 2 from the origin. There are only finitely many integer lattice points then within this distance of the origin. So there are only finitely many possibilities. There are only finitely many cases. So that's this case. There are only finitely many possibilities, and it's because the space perpendicular to the canonical class is negative definite. And this one is similar. If c squared equals negative 1 and c dot k equals negative 1, then let's see, I want to take k squared times c minus k. This is in k perp. If we intersect with k, no, I guess I want that. So k squared minus, yeah, so this will be perpendicular to the canonical class. But the self-intersection is going to be equal to, let's see, so it's perpendicular to k, but it meets c negative 1 times. So I get this negative and then kc, so I get another negative k squared. So this doesn't depend on c, it just depends on the canonical class. And so again, using negative definiteness of the space perpendicular to k there can only be finitely many solutions for this thing, and hence finitely many solutions for C. So there are only finitely many possible classes C. So that's the reason that the set of negative curves is finite. And in fact, to save you the trouble of working this through, here are the possible solutions. Here are the possible classes. Now, these are not necessarily in the negative set, but if something is in the negative set, it will have to be one of these. And so the first thing is, if it meets k negatively, negative k negatively, the only possibilities, instead of writing them like this, actually, I want to go so I want to take basically the class of a line minus a bunch of blowups where these are distinct and j is greater than or equal to 4. It's awkward to write this. So let me write this in shorthand notation as, let me just put in the coefficients. And so I'll write this as 1, negative 1j. So this just says that the coefficient of the h is 1, and I have at least j of these, and they're all negative 1. So I'll use that as a shorthand. So another possibility is I have conics that go through at least j of the points, where j is greater than or equal to 7. So those are the cases where this is true. And then we have the cases where c squared is equal to negative 1. Those possibilities would be a line through 2 of the points, a conic through 5 of the points, a cubic that has a double point and also goes through 6 additional points, and then we have quartics that have 3 double points and go through 5 additional points, quintics that have 6 double points and go through the remaining 2 points, and then finally a sextic with a triple point going through the remaining 7 points with multiplicity 2. Now, in fact, these always represent effective divisors, but they might not always be irreducible. And if they're not irreducible, they won't be in the negative set. C squared equals negative 2 is a little, oh, I forgot some. Of course, the blow-ups themselves have self-intersection negative 1. And finally, we have the negative 2 curves. And for the negative 2 curves, we have a line through 3 of the points, a conic through 6 of the points, and a cubic with a double point going through 7 additional points. So those are the only possible curves of negative self-intersection which can be irreducible. So this solves the Velasco-Eisenbud problem. for sets S contained in P2 with S less than or equal to 8. You just have to determine which of these curves are effective, and there are only finitely many possibilities, and for each one it's a finite computation to determine if it's effective or not. And these will generate then, together with the anti-canonical divisor, these will generate the effective submonoid. And then you have to turn generators for the effective submonoid into hyperplane boundaries of the polyhedral cone. But it's at least in principle a finite decision procedure for answering when multiples of a class are actually effective or not.
Can you explain this last item was a paper?
Pardon me?
The last item was a paper or comment or some conference?
Oh, give a reference for this?
Yes, the reference last item.
You see, you told me yesterday.
Letter or conference or paper or report?
There isn't one at this point.
Yeah.
I mean, the problem only came up a month ago. So
A month ago.
yeah. Yeah, so Velasco sent me an email note and asked, does anyone know if there's such a procedure? And there, it doesn't seem to be known. I mean, I think it's a fairly difficult question in general. And so in thinking about it, I can see in certain cases that there is a finite decision procedure. But in general, I think it's quite hard. In fact, well, let me give you a specific example. So here's a specific example with more than 9 points, which is unknown. So what if S is equal to 9? I'm still not completely sure. I think there is a procedure. But I'm not completely sure. The problem is I haven't had a chance to write the details out carefully to convince myself that it will work. But I think it's reasonably likely that there is a procedure when S equals 9. Even though, in this case, the set of negative curves is not in general finite. So the submonoid, the effective submonoid, is not finitely generated in general. But it's as close to being finitely generated as it can be when it's not finitely generated. It's fairly well understood. So the most interesting case is actually S greater than 9. What if S is greater than or equal to 10? And in that case, suppose you have an element of the divisor class group. If f dot h is negative, or 0 in fact, well, let's say it's negative, then well, h is a Neff divisor, and so if f dot h is negative, rf dot h is also negative, and therefore rf is never effective. If, however, f dot h, well, let's say f dot h is equal to 0. If f dot h is equal to 0, then f is equal to something of this form. I usually like to write it with a negative sign here. It's possible that m is also negative, so this could be positive. But in any case, f has to be of this form for some mi. Hence, f is in the effective submonoid if and only if mi is less than or equal to 0 for all I. So this is easy. The coefficients here have to, the negative m's have to all be non-negative for this to be effective. And if f dot h is positive, then we get the following inequality. So this is just Riemann-Roch for surfaces. This side is going to be t plus chu choose 2 minus the sum of mi plus 1 choose 2, summed from I equals 1 to s, where f is equal to th minus So I was using this expression yesterday. This expression really is just a version of Riemann-Roch. And so if f dot h is I meant to put in one more thing. If f dot h is positive and f squared is positive, then this implies we have a quadratic term which is positive and a linear term. The quadratic term will predominate when r is big enough. So that will tell us that r times f is effective for all r sufficiently large. If f dot h is positive, but f squared is equal to 0, then it's not known. And let me give you a specific example if you'd like something specific to work with. So let S be 10 generic points of P2. Let F be the following example. 13 minus 5 times the class of the first blow-up minus 4 times the classes of the remaining blow-ups. Is R times F ever in the effective submonoid? It's not known, but note that f squared equals 0 in this case. In fact, I emailed this example to Roé, and I asked him, can you figure this out? He thinks that he can. So maybe soon it will be known. But what he's doing is he's applying the Chiliberto-Miranda method to this problem to see if he can determine whether or not it eventually will be in the effective submonoid. But after several weeks, he hasn't yet given me an affirmative answer. So if, however, he does this one, let me give you another one. So the next one is, I'm just a little worried that tomorrow he's going to email me and say he's done it. But here's another one. 111H minus 36E1 minus 35E2 minus 35E10. This also has f squared equals 0. And the problem is, at this point, Roe does not think he will be able to find a single procedure that will work for all of these. What happens is he has to do it ad hoc for this one, ad hoc for this one. And if he does this one, I have another one. There are infinitely many of these. The key here is that the multiplicities are all equal except the first one, which is one more. And so essentially you get an infinite number of solutions with larger and larger integers from Pell's equation. And so I can keep generating these much more quickly than he can solve them. It would be, in fact, if you could show that all of these are never in the effective submonoid, you'd have a proof of the Nagata conjecture. And so it would be wonderful to be able to do it, but it looks hard. Now, what Nagata did, I'll finish with this. Clearly, I'm not going to get to matroids, but let me just mention what Nagata did. What Nagata did was let S equal 10 generic points. No, I want it to be, let's say, 16 generic points. No, let me say S is going to be little s greater than or equal to 10 generic points. And let F be some multiple of the class of a line minus the blow-ups of all of the points. If f squared equals 0, what Nagata did was he showed that Rf is never in the effective submonoid. But the difference is he was only working with a class where the multiplicities are all -1. I mean, they all come with 1s, whereas these classes have bigger multiplicities. What happens here is if f squared is 0, then that implies that t squared minus s is equal to 0. So s is a square. And the case that s is a square is it's tricky. He had a very clever argument, but it's definitely easier. And so he used the fact that s was a square to get this to work out. Essentially, what you can do in this case is it's easy to find a curve which is effective by specializing the points to a curve of degree t. In these cases, it's not clear how to specialize the points to get something to work with. So the difference between what Nagata did and the general question involves being able to work with curves of higher degree, higher multiplicities. And so that's what is making this hard. All right, well, I think I should stop here.